Okay, so again, I'm David, this is Claudio, we're from Atigeo. And what we're going to talk about today is some of the work we're doing on natural language with UEMA. So basically what we're going to show in the next 10 minutes is a fairly straightforward pipeline where we ingest data. You can read just straight Spark data ingestion or Spark streaming. Then we build a UEMA pipeline, which basically is it's a Java-based framework, although we use Scala here, to be able to annotate and semantically understand grammar and text. And then the results we push into two places. We push it to Elasticsearch and then put a REST API on top of it so that applications can use the results, right, and query with sort of with interactive response times. And we also send it just to Spark SQL so that we can do other machine learning modeling on top of it. With UEMA itself, you have some of the annotators that we use. And basically, what happens is we're dealing here with medical records. And when you're dealing with medical records, what you usually know about search, which is basically based on TF-IDF or keyword matching, is pretty useless. Because what I need to be able to do is differentiate between patient has X or patient positive for X, versus patient does not have X, or patient thinks they have X, patient is really concerned about X. Patient definitely had X when he was 5 years old. Patient's mother, therefore patient strongly believes that they may have it. And the result, if you look at the keyword of specific symptom or specific disease or specific drug by itself, it doesn't answer the basic questions like find all patients that are on this drug and are showing this symptom, right? All the patients that that had this experience, all the patients that are positive for this lab, and really the basic semantic questions that you need from the test. So some of the annotators you see here are basic things like detecting section, right? So the this section detection, and then sensitivity, so it's positive, conditional, speculative. Then also looking at units, so extracting lab results, times, and dates. So now I'll hand off to Claudio to talk how we actually do it and actually show a live demo of the system we have in play here.
I'm trying at least.
This is a live demo, so there's no warranty on anything.
Okay, so what we have here is on X-Patterns we have this way of creating a workflow composed of different stages. What you see here is a data stage where we literally pull the data from, in this case, SFTP, and then we have a shell stage where we are executing a Spark, a jar within Spark, and we're executing it distributed. So at scale, where we have a configuration that we pass into this one, which is the UEMA configuration file. And if you look at it, you should be able to see a JSON representation of the configs. Let me zoom in a little bit. So it's all the annotators that we've been talking about briefly. In case I can zoom in. Okay. So you can see the sentence detection, section detection, the token annotator, the stopwords annotator, so forth, so forth. At some point, the concept annotator was just a lookup into an ontology, so it retrieves the concept from there, and all the others that we listed on the slide. Pretty much what this tool allows you to do is you have a configure file, you just clone this job, change the config, run it again, you have different set of annotations as an output. And you do this at scale, so that's the input on HDFS, it's the output on HDFS. Now let me very, very quickly show you how the input and output look like. So, okay, this is the input, right? If I look into one of the files in the input, this is what I get. I get, pretty much, this is, by the way, the data set we've been showing here is a de-identified version that we curated from the Mimic data set for people who are interested in that. We can share that at some point. And so you have an EMR, an electronic medical record, and this is one of the hundreds of those that we have as input. And then the output, obviously, of that processing pipeline, which is this one I've showed here, is two Hive tables in this case, an annotation one and an assertion one. An assertion is literally just a grouping of annotation on the same place in the EMR. So for the same positions in the text, you have a bunch of annotators grouped together. And then this job here is publishing it to Elasticsearch from Spark SQL. So let me show you some cool things you can do after you're processing this. So obviously a select star in a table will give you all the assertions, and these are some of the attributes of those assertions, like the normalized section, the subject if it's the patient or somebody else, the concept type if it's social, concept, gender, whatever, out of the ontology, and then the not normalized concept value. And this is important because sometimes terms that appear in a particular text are not normal. They have to be normalized to from different versions to the same root. And then obviously the source can be a list of sources within, we can have multiple ontologies, so you have a list of the source for every node pretty much. Polarity and all the other attributes, I don't insist on them, right? And obviously the text position, because this is highlighting you where the text, that annotation came from. And then, as I've told you, you can do some interesting things with it now that you have it. One of them is just, simple SQL queries where you can go and say, give me, all the concepts, and this in case is just the DF if you want the document frequency, where the concept type is a body part, and the polarity is positive, and the subject is the patient, right? So you have all of them here. You can do some analysis, see what's going on. Later on, you could go build a classifier, do whatever with it more interesting, but you definitely need to have a way of extracting the information out of the unstructured data, and this is what this does. This is the part where I'm publishing to Elasticsearch. Literally, we are mapping into an index all the fields in the table I've shown you, and this is where you're selecting, what you want to map to what you want to tokenize, if you just store it and not search. And obviously, after you do this and the job runs, it publishes a REST API, and you can actually query that REST API. I'll try to do. Okay, so this is a classic query. If I go and put in here, let's say a new term like a very used term in medicine called blood, then obviously you have interesting results, and some of them do contain blood. It does happen that this one is an end word that has blood pressure, but I can guarantee you that if you look at some page, but because you use an ontology and pull things out of it, then there is a relationship with that. You can get interesting terms out of that. Are we in the? Good. Thank you.
All right. How's it going, everybody? Yes? No? Woo! Come on. Bright, shiny face. I'm wondering if people are alive or not. So. Huh? Cool. Awesome. All right. Okay, and my machine did not blow up. Sweet. Woohoo! Oh, I need to plug in. Sorry. All right, give me 1 second, guys. All right. So, hopefully this does not wreck anything. Okay. Cool. I might do a dance or a jig, so I apologize in advance for that fact. So, about myself, just in case, because since Amanda didn't do an intro. Haha. No. My name is Denny Lee. I guess I'm one of the leaders of the Seattle Spark Meetup. I'm previously from Microsoft, as I admitted in front of we actually, Saptech and myself suffered the audacity of actually bringing Hadoop into Microsoft. So we actually were the crazy idiots who decided, hey, there's no big data strategy in Microsoft. Let's bring an open source Linux product into it. Palmer will love this. So yes, okay. So we worked together. We fought together, not at each other. I'm just we together. Okay. So to go ahead and build that. He left for Hortonworks. I left for Concur roughly at the same time. I had a really cool title called Senior Director of Data Sciences Engineering. Cool title, eh? Yeah. So we were doing some pretty cool stuff. We got bought off by SAP, and then Databricks was silly enough to try to hire me. So here I am. Okay. And so what I'm showing is a decision tree analysis using Salesforce leads. Okay. So this is just a pure quick demo of what the standard painful process a data scientist is going to go through. So here we go. So and right now what I'm showing is basically Databricks notebook. The notebook is based off of IPython, just in case anybody was curious about it, except that you can write in Scala, Python, R, and SQL. So for example, if you look at the book right at the top, I got %SQL here, because inside the Scala notebook, yes, John, okay, in the Scala notebook, I'm actually able to write both Markdown and also SQL statements. So for the analyst in me, the first thing I'm doing is SQL. So for example, leads that I've got up here, okay? In other words, the company, these are all fake, by the way, so don't even bother, okay? But, This is the company, this is the state, where's the lead source, okay? In other words, it's from the partner referral, and you don't even worry about the status, but that's the context, okay? When I scroll down, okay, the first thing I'm seeing here is a map of the United States, okay, where the leads are coming from. There's not a lot of leads here. If you actually bother doing the counts, you'll notice that there's only a few. The idea is nevertheless the same, which is, you have a great way to go ahead and just observe and see where the leads are coming from within the United States, okay? And here are the lead sources, okay? So at this point, I'm just running SQL statements because as a person who has the domain background, that's usually what they're going to be able to write. They're going to be able to write a SQL statement, okay? So they're comfortable with that. Cool. All right, first things first, I'm going to do a data preparation. This stuff is basically me just pulling Spark libraries, okay? That's all this. And by the way, this notebook is either, okay, I keep forgetting, is it either available now or will be available in the next week? I forget the timing, but basically anything that I'm showing is not only going to be able to run in Databricks, you'll be able to run it on your own Spark instance. There's nothing about what I'm doing here that's specific to Databricks. It's just that it's easier for me to do it within a notebook. That's all this is, okay? And so what I'm doing is I'm actually just asking for the distinct leads. Now I've switched over to both a combination of SQL statements and Scala statements because as a former data engineer or pretend data engineer, that's what I prefer writing in. I prefer writing in Scala, okay? Why? Because for a lot of people who play with both Spark or Kafka or a lot of these other open source systems, they typically are written from an engineering perspective in Scala. So as a data engineer, that's why we often prefer using that language. Good, John? Excellent. All right. So by the same token, for all of you who are data scientists, okay, you're naturally going to go gravitate toward Python and R. That's understandable. I have other demos for that. Not today, but there are plenty of demos. So it's not like you can't use Python and R. I'm just calling out the importance of Scala. Okay. All right. So the first thing I was doing is categories and leads. And guess what? It is a case statement. Okay. It's a Scala version of a case statement, but it's basically a case statement. Okay. Why? Because anybody who's a data engineer or data scientist or analyst, what are you most likely doing most of the time? Can anybody answer that question? Wrangling, exactly. So basically, you're bored out of your mind, staring at the data, trying to make sense of it. That's what you're really doing most of the time, okay? So all I did here, because I didn't really want to go ahead and try to understand each one of these things, I just categorized it all, okay? So in other words, I categorized it to the lead source is digital, a network referral, or a paper, okay? In fact, after I skipped through a bunch of gobbledygook, that's all this is, okay? Basically, in the end, that's all I have. I have the three things that are saying it's either a paper's lead source, a network referral, or a digital lead source. Okay, so that's where the leads are coming from. In other words, I sent marketing stuff, and I want to know what the heck is going on with it. Now, why am I building a decision tree? Okay, I'm going to skip to get to the main. Okay, here we go, to the model preparation. Can anybody guess why I want to use a decision tree when it comes to a combination of states and marketing lead sources? Can anybody guess that? Right, explainability, that's definitely one thing. Anybody else can make a guess? Right, categorization, that's another reason, but the other reason that I'm doing is also I'm trying to predict, okay? And by the way, you're gonna get a laugh out of this, the predictions are horrible, okay? But this is also a common approach, common problem, that's actually why I want to show it, because the reality is when you're dealing with lots of data, number one, a lot of it's dirty, okay? Number two, you're gonna iterate a lot, okay? This is not something where, oh, I run one algorithm and it's beautiful and it works perfectly fine, okay? Because otherwise I wouldn't have a job, okay? So the reality is, you're gonna go ahead and try all sorts of, iterate a bunch of times, and again, I'll show you exactly how bad this stuff looks like afterwards, okay? All right, so in the end, I just was running a decision tree classifier. Now in the case of, it's hard for you to see this, so I apologize, but don't worry, we have a video, and again, we're gonna share the notebook. It's 3 lines of code right up here for me to run the decision, all right, to train the model. All of this are the Spark jobs, okay? All this is the output of the Spark jobs to tell me what's going on in the system. In fact, if I actually had an updated system, I could run this in real time, and it actually has this really cool animated GIF and everything, which is really sweet, but I didn't have it installed, so my bad, okay? But the context is that all I'm doing is I'm training the model here, and now this little bit of code here, okay, is basically Right, actually, that's the wrong code I'm looking at. This is the code where I go ahead and actually test that model, okay? And again, you'll notice that it's only 3 lines of code. Basically, I'm simply saying I define a predicted lead source, okay? And I'm going to go ahead and basically take the array of data that is the output of the trained model that I just ran, and I'm going to go ahead and do some prediction. Now, it's a little hard to see, so I'm actually going to go ahead and zoom in. But you'll notice a couple things a little wrong with this thing right away, okay? When I predict the lead source of California, the lead source says paper. Okay, so what's the likelihood that people living in California are going to actually be more, have an affinity to paper advertising versus digital advertising? Fair enough, okay. But most likely where most is sort of San Francisco-ish, where we have a tad bias toward there. Okay, so in other words, already the model's looking wrong, okay? But it's going to look even wronger soon, okay? So, all right, so but we were able to predict, interestingly enough, Alabama is digital. A little odd, okay? Illinois network referral, that actually made sense, okay? All right, so, but now what I'm going to do here is I got 2 approaches here, okay? I can either generate the predictions now, because since there's only 50 states, I can either go ahead and generate the predictions, or I can create a function that actually accesses the Spark SQL. Now, the reason I'm calling this out is because what's sort of cool about that statement is that you, as a data engineer or analyst who's used to writing this stuff in SQL, up to this point, you're actually able to write SQL statements. That's what you saw before, okay? The data engineer or the data scientist that's writing stuff in Scala or in Python or R, they're able to write all this stuff in their preferred choice of language. What's cool about this is that because I can either create a function or generate a new table based on this data, that means the data scientist and data engineer, or the analyst, the person that's writing SQL and the person that's writing Scala, they're actually collaborating with each other. Realize they're collaborating. They may not realize what they're doing, but that's exactly what they're doing, okay? And that's actually what's really cool about from this standpoint, that because you're actually able to get people to write in their preferred language of SQL or Scala or R or Python, they're actually able to focus on the data problem itself instead of actually focusing on trying to get the system to work, okay? And so that's actually what's sort of cool, because in fact, that's how this notebook was created. The person who originally created the notebook was the SQL guy. He went ahead and actually figured out how to get the data out of Salesforce, and then it was actually a data engineer that went, a data that went in and actually tried to make sense of it. They were collaborating without actually knowing. We have a comments feature, which I'm not going to show right now, but allowed them to go ahead and actually add comments to the notebook so they could actually figure out what was going on. Because the reason why is because one person was in one location and the other person was in basically another remote location. So they actually never met each other to build this notebook. Okay? But so what's cool about this is that now they create a table, okay, together, because you either generate the new data or using a function. They're able to go ahead and say, well, California, the actual value, the lead source is digital. The predicted is paper. Again, that's wrong, but that shows you the state of the data, okay? Florida, paper, Colorado network referral paper. So you have that quick list right there. And so then when you compare the actual versus predicted, so this case is for paper. This is what we, the actual values. Almost done. So. And here's the predicted. So you look at the maps, they look pretty similar to each other. So guess what? I guess our prediction for paper is not bad, okay? On the other hand, our prediction for digital looks like this, okay? Sorry, our actuals for digital versus this. Here's our prediction. Notice that we're slightly off, okay? So the quick call out basically is that we got this one notebook. Both our data scientists and data engineers can actually work together in their own preferred language. This is the standard iteration. And so basically, how you solve this problem, by the way, a function, actually, sorry, John, a Python function that actually allowed us to go ahead and do a better job predicting on the digital side of things. Okay, so that's what's missing inside this notebook right now. And so we actually already have it, just I haven't put it here. But anyways, that's the quick call out, and this is how we basically do decision trees and machine learning all within the context of Spark on data. Okay, that's it for me.
Hi, my name's Deborah Siegel. I work at the Northwest Genomics Center, and that's at University of Washington, and we're also a part of an organization called the Centers for Mendelian Genomics. for this, I wanted to learn and to integrate a few different components to use Big Data Genomics Atom, which is a genomics platform that runs on Spark, as well as Spark ML and SparkR, actually. On the field purity spectrum, I'm holding the octopus there. That's very accurate. Except biology can also be really multidisciplinary and draws from these other fields, as we'll see too. Okay, I have a quick refresher on the representation of genomic data. So humans have 2 copies of most of our chromosomes, and that's represented by a sequence of letters. And each position will consist of one of four letters. And we also have a concept of a reference genome, which is a sequence which contains usually what's the most commonly found letter there. So for most of our genomes, the letters that we have in all the positions will match what the reference genome has, but we do also have variation there. So in this example, this person has 1 copy of the G, which is the reference, and 1 copy of an A there, which is an alternate allele. So there's really 3 options there. A person can either have 2 of the reference, have 1 of the reference and 1 of the alternate, or have 2 of the alternate. And so in the analysis that I'm going to show, the data is represented with Manhattan distance. So for each person, depending on how many alternate alleles are there, they'll have a 0, 1, or 2. Before I want to share with you the analysis I did, I just want to set up a little bit more context. The motivation is really that these variations can cause diseases in humans, so we want to know, we want to find out what the variations are that cause diseases and find out what those are. The scientists that I work for study a lot of the rare alleles causing Mendelian diseases, which is up on the top left of that diagram. And there's about 6,000 Mendelian diseases that are known right now, and about the causes of about 4,000 are known. So we have 2,000 to go, and we're closing that gap. Right now, what I'm going to talk about, though, is down in the bottom right corner of this, which is common variants implicated in common disease. One thing about this space is it's been described as trying to find needles and stacks of needles, because we have a ton of data. We can find the variants by sequencing, but we're trying to figure out which are the ones that are causing the diseases. So which are the needles, that are causing diseases. One of the techniques that is used to do this is a dimensionality reduction. Excuse me. I wanted to say also that one of the things that confounds finding the causal variants in this case is not accounting for population structure. So you could think about it with 2 points. One is that population structure you could think about it as geographic location. That's kind of what population structure means in this case, because people who are close together kind of tend to get together, and so there's a population structure in that sense. But then also, diseases may be more common in one population than another, but not because of the population structure. So then you get some spurious associations with variants, and you want to take those out. So you can adjust that by doing a dimensionality reduction. One interesting paper to show that happened is these authors did a principal dimensionality reduction, and it turned out, just a refresher, principal looks for the direction that the data has the most variance. And so in this case, they found that the 2 top directions where the data had the most variance actually mirror geography within Europe really well. So this is the plot of the 2 top principal components analysis, and you can actually see the Iberian Peninsula and the Italian Peninsula there. They were able to distinguish between people whose grandparents originated from Ireland versus Great Britain. Okay, for this that I want to show you, I used public data from something called the 1,000 Genomes Project, which is available on S3 on Amazon Web Services for anybody to use currently. It's a wonderful resource. I selected some populations to work with. I selected Americans of African ancestry in the USA, some Yorubans from Nigeria, some Utah residents with European ancestry, some British, some Chinese, and some Japanese. And the feature space we're talking about is each person's genome has 3 billion positions. I only did this analysis of chromosome 22, I'm hoping it'll scale. So chromosome 22 has 50 million places. In general, we have 1,000 variants, and we're only looking at it, so that's about 500,000. Common in our sample. There are more sophisticated that I did not for this analysis, but eventually the point is to do a PC and take a look. Now I want to talk about the Atom project, because that's why I was really excited to do this project. So Atom, Big Data Genomics is a collaborative project that's really exciting. It's got a few components. One is a file. It runs on top of Spark. It offers a file format that uses Avro and Parquet. And it also offers a command line interface and an API. And I used all of those in this project. I created this representation which doesn't contain all the fields, but Atom deals with this kind of data on several different analysis levels, from raw until complete. This project is very much downstream of a lot of it, but I used mostly the genotype and the genotype allele and the variant. And here I also show there are not only file size these are some file size efficiencies that I got from doing it. So the variant call file, which is the typical genomic format, is 2 gigabytes gzipped and 14 unzipped. And then in Atom Parquet, it was less than a gigabyte. But there's other efficiencies also. This is just in terms of size. This is the workflow I did for the project. There's 3 phases. I have the Spark Atom phase, where I took the VCF file and I used the Atom client tools to create a Parquet file of the genotype objects. I then filtered those by populations, and I created a case class of sample variants, and I used that case class to filter for my complete data and common variants. Then it was ready to go into the machine learning phase, where I used Spark ML, which is a wonderful API to use data frames as input to machine learning. So I created RDD of sample ID and ordered those by the alt-allele counts. So I'm creating my input data. I turned that into a data frame with a schema. Then I used ML component called vector assembler to turn my features into a vector. Then I used the ML component to fit my PCA model, and then transform or project my original data points onto the PCs. From there, I had to do a bit of slicing and dicing because, and this is by no means optimized workflow, but I did want to use SparkR to visualize my results. Thank you. So SparkR does very well to read Parquet files from HDFS, but it doesn't currently read vectors, and the output of the ML pipeline was vectors, so I did put that through a little bit more work. Oh, I was going to do a demo now to show you the visualization, but I do have a slide of it in any case. So I did, this is the result that I visualized using SparkR, reading in the Parquet file from the ML pipeline. And I was really surprised because although I didn't do the analysis with all of the bells and whistles that I would have, but my sample still segregated it in a fairly geographic manner, in my opinion, because I do have the Chinese and Japanese in the east, and then in west I have Western Europe and the Americans with Western ancestry up on the top, and then the African Americans and the Yorubans there in the middle. So I thought that was pretty interesting. So we literally have, our genomes literally encode a geographic map. This is just from genome data. And I just want to thank Northwest Genomics Center and Amanda Cassari, and actually all the people at Big Data Genomics for their help. And I also, there was a blog post where I got some excellent ideas for how to work with the data. Thanks.
Sorry for an interruption. My name is Emad Surush. I work at Dato. It's a company that builds machine learning frameworks for data scientists and software engineers. So today I want to talk about how to build a sentiment analysis classifier using two great platforms, Atigeo Spark and GraphLab Create. So let's have a quick introduction for each of those platforms. Atigeo Spark it is support for wide range of data engineering tasks. And it also provides a rich language binding from Java and Scala to SQL and Python. And the core data structure that powers the Apache Spark is a resilient distributed data structure called RDD. It's a highly scalable in-memory fault-tolerant data structure that enables distributed computation. So that was a quick overview about the Apache Spark. I'm sure most of you know about that. So let's see what the GraphLab Create. So GraphLab Create is the machine learning platform that helps the data scientists and software engineers to create intelligent application quickly and at a scale. GraphLab Create supports a wide range of toolkits from text analysis, deep learning, image analysis to graph analytics and chunk prediction. The core data structures in the GraphLab Create called S-Frame. S-Frame is a highly scalable out-of-core data structure that is optimized for the machine learning task. It's also open source. So let's talk more about what is S-Frame. What's the main principles in the design of the S-Frame? The first principle is the graceful degradation of the S-Frame. So no matter in what environment we are, if we have limitation in the memory, the S-Frame should work. The second principle of the S-Frame data structure is that it has support for a wide range of data types. It supports the strongest schema, integer, double, string, image, and so on and so forth. And it also has support for weaker schemas like a list, array, and dictionaries. And the third principle in the design of this data structure is that it has columnar architecture, in a sense that it makes the feature engineering for the ML task pretty easy, and also makes the and also enables the vectors of optimization and also enables the aggressive compression. So let me show you how a frame works in a very simple example. Here we have this frame with a column. So when the assignment happens, there's no copy between the data. We only change the pointer from one column in the frame to the other one. So the other operation that we are doing, we are trying to subtract one column from the rating column from the first frame, from the second column in the rating column in the second frame, and we store it in a data structure that we call S-array. S-array, if you want to think about S-array, is an external memory NumPy array, and the S-frame is basically a collection of the S-arrays. And finally, we can just assign the new diff column to the second S-array, and no copying between no copy or movement of the data happens here. We only point to the right location of the data. So that was just a quick demo about the S-frame. If you want to know more about the S-frame, please look at the S-frame presentation in the PyData that was done by the Yu Cheng Lo. So the main topic of today is the introduction of the Spark S-frame package. So what I want to argue is that the most challenging part of the ML is getting the right data in the right form. And the process of training models is most efficiently done if we use the specialized ML tools that leverage the data structure of the ML algorithm. And we know that the Spark is a great platform for bulk data ingestion and data transformation. And GraphLab Create, by using the S-frame in the backend, is a great platform for doing ML tasks. So that would be great if we can blend the best of these two worlds together and achieve a single task using these two platforms. This is the hard problem in a sense that these two platforms are written in completely different environments. Spark is mainly supporting the Java and Scala. Is natively supporting Java, Scala, and is a JVM stack framework. Dato is mainly written in the C++ and Python. And on the other hand, they are fundamentally designed differently. The SparkR is a row-wise data structure, while the S-frame in the GraphLab Create is a columnar data structure. So what we did in the last few months, we were working on the project called Spark S-frame that bridged this gap. Spark S-frame package unites the data ingestion and processing capabilities of the Apache Spark with the sophisticated machine learning tools of the GraphLab Create. It's an open source package. It's the BSD license, and you are welcome to go and download the package and try it. You can change it and share it with whoever you want. And it has support for both Python and Scala bindings. So this is just a simple example of how we can use the Spark S-frame package in the GraphLab Create. This is the Python binding one. So you see that in a few lines of code, I can use the from RDD and the to Spark data frame and translate back and forth between the data frames and the S-frame. So next, I will show you a quick demo how to build a sentiment analysis classifier using a few lines of code using these two products. So I'm using IPython just for the demo purposes. So can you see that? So here I created a Spark cluster in my machine, so it's a local Spark cluster just for demo purposes. So I already ran the Spark, so the Spark instance is loaded. So I will pass those. So the purpose of this demo is to create a sentiment analysis classifier. So I load the data set that contains movie reviews, and we want to detect what is the contextual polarity of these reviews. Is it positive or negative? So first I ran this part. Let's take a quick look at what this data contains. So this is basically a raw data. So remember the data ingestion and data transformation that the Spark enables. This is a tab-limited data. So we first use the Spark to just split it for our column. This is what we get. We have now a Spark that is represented as a list of strings. The first one is the ID of the review. The second one is just the sentiments or the labels of those reviews. And the third one is the movie reviews. The goal that we are using a Spark here is to create a bag of words from these text reviews. So I will go. So I won't run the script just for the interest of the time. I will just show you how does it work. So in the next command, I'm trying to just trim the white spaces and split it on the single space. And then I use the flat map. The current tuple is the index and the list of the words, and I want to create a list of indexes and the words. So this command will create that one, and come on. And the next part is adding the count value to each of those tuples. So this is just the process of creating a bag of words. Let me skip this part and go to the more interesting part. So after we do all of those transformations, the final result is this bag RDD that contains the IDs, the sentiments, and a dictionary that contains all of the counts for the word, and that has the key as the word and has the value as the count of those words. And then after that, I use the Spark frame package to translate this RDD to the S-frame. So let me run this part. This will take just a few seconds to finish. And then, here I'm just creating the data frame. After that, I use the GraphLab to do the conversion. So this is the part that we use to translate the S-frame to the RDDs. And then when the S-frame is created, we can fit it into the sophisticated ML toolkit that GraphLab provides. Here is a classifier that decides which classification implementation they should use for this particular data set. Here it shows logistic regression. to classify this, to train this model. And then when the model is created, we run it on our test data set to get the accuracy. So here is the accuracy is about 85%, so it's good for a single, in a few lines of code when we create. I just want to show you in a few seconds is we have so I only take a snapshot Scala commands that we can use to do the same process, and then use the Spark Spring package to translate the output to a Spring. So this is with all the examples how to build this package and create a jar file that you can fit to your Python process or to your Scala process. Please download that and give us feedback. So one valid question that you could have is, I have my data in my Spark cluster. I don't want to take my data out and bring it in a different environment. When you convert the RDD to a Spring and Spring to RDD, your data is still in the cluster. You can train your model on the data that you already have in your cluster. We have the server solution that helps you to deploy the GraphLab job on the Spark cluster. Thank you.
This is my slide. So my name is Brian. I work for Cloudera. I live in North Bend. I'm a system engineer out here. I like data, microcontrollers, walks on the beach. It's supposed to be a joke. Maybe not a good joke, but it's a joke. Thanks for inviting me. Really appreciate that. It's very nice of you guys. Lightning talk. I got 3 things here. One thing we see a lot, it might be of interest to this group, is recommendation engines. So I'm going to cover that in kind of a fixed open source product that we have that comes out of Cloudera Labs. I'll talk a little bit about that. I'll talk about the architecture and then typing on keyboard. That's what I'm going to do for 99% of it. So that is kind of my intro. So I'm just going to get started here. So from a recommendation engine perspective, it's a really common use case. We see it quite a bit. You guys probably have seen maybe similar requests in your organizations. There are a number of different use cases actually for recommendation engines and the machine learning behind it. Some of those things, the obvious examples, are ones we experience as consumers. You might also like, et cetera, et cetera. There are actually some other interesting use cases for it as well. I mean, and people are kind of using it in creative ways, so you can kind of let your imagination run wild a bit. But I mean, you can think of things that I'll show you here with some of the API endpoints that might be interesting, where you can think of maybe pharmaceutical recommendations. You could think of different colors, or things that you want to suggest to people. Maybe just some data science experiments. So I'd be interested in hearing from you what other use cases you have for collaborative filtering and recommendation engines. Specifically, Oryx, and this is actually on its 2nd version. This is all on GitHub. It's all open source. It's developed by Sean Owen, who's a great resource at Cloudera's data science team. It's out of the Cloudera Labs, but this is just a great place to kind of get started if you want to see like a modern implementation, specifically a Lambda-style implementation of a recommendation engine. And just kind of focus in here. Hopefully you can see that okay. The graphic kind of down here at the bottom, because these are the layers we're going to start up. And so it's using Kafka. It's using Spark Streaming. There's also a serving layer that has a RESTful API endpoint. I'm going to show you all this stuff as well as ingest in 7.5 minutes. So. Okay, I'm logged in here. The first thing I'm going to do is I'm actually going to start up just the tailing process on my Kafka message queue. The second thing I'm going to start up is what you saw in the diagram, which is called the batch serving layer. the batch is 1/2 of that Lambda style architecture. I'm also going to start up what's called the speed layer. So you can think of these, the batch and the speed layers, kind of bottom here is one is doing kind of the heavy lifting of the model, the other one is doing streaming model updates as they come through. And then up here, I'm actually going to start up the serving layer, which provides a RESTful endpoint, just HTTP endpoint for ingest. Also, it does have a user UI as well. So we see these couple of things starting off. If everything works well, yeah, how about that? So here's some of the endpoints that are already available. I haven't done anything special to this. One of the things I really like Oryx for in general is it's a great kind of reference architecture, and it's something that's already built and you can use. So maybe even if you already have a recommendation engine, it's something you could use to even baseline your own to see if you could get similar outputs. And if you want to switch between alternating least squares and you want to move to k-means or something else, those are all available in the models. So just a quick kind of scroll here, and I'm going to try to make this if I can. Whoa. A little bit bigger. Okay, good. So like right now, I have a very limited data set, but I'm just going to click most popular items and hopefully get a result set here. And so they're just key value pairs, right? So if I shrink this down a little bit more and I see like most active users, so user ID 405 is up top, okay? So let's go, I'm going to go and send some more data to this through the API endpoint. So what I'm using for data, we see a whole bunch of things. You see the Kafka message queue start to fill on the top right. In a second here, you'll start to see the model processing take place. You already see it in the bottom left. It's already starting to interact with that data. You're seeing it's actually throwing it back on the message queue, top right, for the updates. And then I think I have it set to 60 seconds, but it's configurable on the bottom right here for the batch job. So hopefully within a reasonable amount of time, it should kick off because I have 4.5 minutes left. Bang, there it goes. If we went back to our UI, so it still says 405, but now it says 505, so I get a different key value pair. Now we see the model actually starting to get published in the background, persisting the model to HDFS, where the updates are just taken in and being pumped back onto the Kafka queue. So you see more activity on the message queue, so now the model's been updated, and so it's republishing the model. So let's look at most popular items. Or let's just pick a user ID. Like I'll just pick user ID 100. And so like he's got a pretty strong recommendation for 272. So that doesn't mean anything. So I'm using the Movie Lens database just as a sample set. I can go over here. I have an Impala table built to do the lookup of what the movie title was. So it's Good Will Hunting. That data load finished, fully processed. We'll go back and just start pumping some more data through there. Still says 272. Hopefully, if all the stars align, we ought to see when the next model publishes, we should get a different recommendation. Okay, so activity on the batch side, activity on the streaming side. Add a couple spaces to that. So these are both the speed layer and the batch layer are Spark stream jobs. So while that's processing just for a second, just to prove it, there's no man behind the curtain. So you actually see him running under yarn here. So it is actually not smoke and mirrors. Okay, it looks like that one was good. So here's the test. So we're at 272 right now. 301, how about that? All right, yay. So now let's see, now let's go do a sanity check here. So I have no idea what in and out is. Maybe somebody else knows what that is, but those are the two movie titles that we saw recommendation-wise. And so you could just go down this stack too, like 301 and 315, for example. No idea what that is. But there's some other kind of interesting things here that you might see in these endpoints. You can see most active users, popular items, all user IDs, for example, just to prove that I actually do have a number of different items in here. I think there's like 1,600 different movies. So you can see the huge list here. But hopefully that kind of gives you a feel for a Lambda style where you have a batch and a speed mode. It's quick, relatively easy to configure. It uses Kafka as its transport layer, both for the updating of the models and the publishing of the models. We've just seen a lot of interest in that. Just to give you a little bit more context, all of this that I've started up is just done with a configuration file. And for this example, I'm using alternating and least squares, which you can. There's other examples for k-means and clustering if you have that kind of use case. And you hopefully see here that the configuration is relatively straightforward. There's just some yarn parameters specifically for the batch job, and then similar for the speed layer, which is that real of the models. And I have 20 seconds left. I'm done.
Hello, so my name's Amanda Kasari, and like I said, I'm a senior data scientist for data, and one of the reasons for that was because I wanted to make sure that I was showing things that would not reveal any information, and quite honestly, I didn't prepare in enough time to make sure I had data that would do that. So, as I think Deb mentioned before, or mentioned in her slide, and failed to mention loudly, so we're currently working on a project together that's looking at doing data analytics with the new SparkR release, and we're pretty excited about that. Most because we've done some work helping people learn our in doing data. Us now that Spark most going to reach your community interested in data science and analysis and data analytics, but maybe don't have as much experience or don't feel comfortable Python or Scala or Java. So what I wanted to show tonight was a little bit of kind of what I've been learning working with SparkR, which as the newest API has been fun and sometimes frustrating. And so for the committers out there, we would love to talk with you. This is another point for us hopefully to be able to get in connection with some of the committers, to be able to talk about some of the things that we've been doing and problems that we've been running into, and then some of the things we really love. So one of the things that I really love is that SparkR you can use with RStudio. So if you're used to using that as your introduction to R, you don't have to be from the command line. And I was most interested in finding out, do you get all the benefits that come with RStudio with SparkR? So that's hopefully what I'm going to be talking about tonight. And the machine learning model that's right now is available in Spark, which not everybody really gets excited about these days, and I find that a little bit sad. So hopefully a bit about how generalized linear models are great for different things. I'm going to be showing the canonical iris example, and for that, it's an example that's a lot of literature people are used to seeing in R, and they're used now I can show it in SparkR. So I did this using a Markdown document, so it is the RStudio Markdown document, and then just for fun, I also included a Shiny component. I didn't do the actually it is the interactive Shiny component. So it's an RStudio document created in RStudio, active visualization at the very end. And I didn't have to do any special setup to get all of these things working together. So there's a little bit that you have to do up front to get SparkR working out of RStudio, but really once I did that, everything else integrated quite well. So I was really excited. It in, using the iOS presentations as well. So it'll take a moment. I think GLM was also the first thing that Spark brought up for MLlib and for other projects too. So it's kind of the gateway into bringing more ML into Spark. So I'm really excited to see where the project's heading with this, especially because being able to do that pipelining, I think as Denny showed earlier, using SQL and Scala and Python all together in the same notebook, now bringing that into R and being able to use basically different components of Spark for different parts will be really powerful for people and for data scientists and analysts, because now if you need to be able to do heavy lifting and Scala's most performant, then you can work with people to do some heavy lifting with Scala on one part of your Spark job, but you can do things that are higher level machine learning or visualization with other parts like SparkR. So just quickly on what a generalized linear model is, everybody goes back to y equals mx plus b. So it's the idea that you can have a prediction or an estimator, you can have an outcome, and then you can have these sets of variables, so that's the x's, and then you'll have these sets of weights. So the beta 0, the beta 1 is this idea of how do you actually start weighting through the variables, and the error variables are not normal. That's the linear model framework that you're getting extended with the generalized linear model. So in R, we're using the stats or the and so for those of you that are not familiar with R Markdown, this essentially is, it's a notebook or it's a document that's created, and it has been created actually by running the R code underneath. So I can show you that a little bit more later if you want to see. I've suppressed warnings and messages and a lot of things so that it shows pretty. But essentially, when I knit everything together, I actually ran the R code. See? So all of the result, this is cut and paste. This has actually been created when I press the knit button. And then as well as all the Spark actually ran everything already from that. So this is just going through, once again, one of the kind of classic iris models. Can you predict? This is an example of a bunch of data of irises, flowers. So if you have a collection of all these measurements of flowers, can you actually predict the length of the sample based on the width and the species? And so you can go through and you can build a model using GLM in the stats package, plot the model and kind of see the difference between the residuals and then the actual fit of behavior. Now, GLM and SparkR, there's a few things that are available that it's not as extensive as the GLM package right now in stats or in GLMnet, but the things that you do have available, you have the formula. You can do two different error distributions using family, and that's Gaussian and binomial. The data that you're going to be using is actually the SparkR data frame for training. And then there's regularization and then the alpha parameters as well. And more about that documentation is listed in both the SparkR and in the R documentation. And so just a little bit more on that. So when we're talking about the difference between a linear regression and then the generalized linear model, the linear regression, you're assuming that there's a normalized distribution in your errors. For the generalized linear model, you don't have to make that assumption. So you can use different kinds of error distributions to be able to describe actually what's happening in the world to be able to do this linear fit. So like I said, I basically took what I had just done in R. So the things that you do in RStudio, you do have to set your system environment variable to point towards the Spark distribution that you want to be using. I'm running everything locally because presentations and demos are kind of tricky doing things from the cloud. Big thumbs up to everybody who did that tonight. I always do things locally because I'm never sure about internet connections. You want to load the path as well as the library for SparkR. And then, just like in every other Spark context, you initiate the Spark context, initiate a SQL context, create a data frame, and then you can create the model using the GLM function. And so the interesting thing, and this is one of the fun things about SparkR, is that all of the time, so you do have to make sure that you're either initiating an action, because if you perform a transformation and not the information on the object and not actually on what you want to be seeing. So summary is one of those things that produces that for this model. You're not going to get a full summary on it until you actually produce an action. But if you go through and you do an actual predictions and then you show the data frame, that actually, the show DF does do an action, so it'll actually take the first two rows off of that. So from the model, I went through and I was trying to predict using the data frame, like I said, what that final outcome would be. It doesn't pretty, looks better actually in the RStudio output, but essentially it'll give you back that table of that prediction, which you can then predictions data frame then to go and create the Shiny application. So what I'm running through here is you can actually see that just using that data frame and then creating, it's actually running an inline Shiny app. If you want to, you can go through and start creating an interactive visualization using SparkR in the exact same IDE that you were creating everything else in. which is really fun. So one of the things about this I really liked was, once again, so if you are a data scientist or you're a data analyst and you're used to working in R, now you can start working on distributed methods in R using the same IDE and the same framework that you're used to, and you can also create data products like visualizations and presentations from your work without having to go in and create all presentations or your work over to another method. So in terms of trying to create things that are iterative methodologies that work on a team basis, I'm really excited about seeing the direction of the SparkR project for that reason. The other great thing about Shiny, which I didn't show here for those that aren't familiar with it, the Shiny project actually produces web applications as well. So you can create standalone web applications that run with Spark on a cluster if you wanted to, and you would have an interactive tool to be able to do that. So just as kind of once again, a heads up towards people that I borrowed things from, cheat sheet is excellent when you're going through and learning. There's some great tutorials, and we'll make sure to post all of these afterwards. Okay, and I think I ran short, which I'm sure everybody's excited about. I always end all of my talks with an appropriate comic. Because as great as linear models are, they're not necessarily appropriate for everything. Okay.